Hi, everybody. I am here in the Sterling College Natural History Room, and today we're going to spend some time talking about skull anatomy and specifically mammalian skulls, and learn about how the anatomy of the skull can give us clues about the ecology and natural history of different mammals, what their lifestyles are, what their diets are, and such. And I want to start by taking a look here at a reptile skull. And the reason for that is that mammals descended from synapsid reptiles. And when the reptile, so this is a modern reptile, this is an iguana, it's not one of our ancestors, but by looking at this, we can see what changes happened in the evolution of mammals from reptiles, and what traits were retained that we can contrast with mammals to learn a little bit more about them. So here is my little iguana skull, and I'm going to hold up a magnifying glass to show you this guy. And some things to notice. First of all, look at the teeth. Notice how those teeth are very simple. They are all the same. There's no differentiation among the teeth. And then another thing I want you to notice is how far back the lower mandible extends beyond the teeth. And so there's this kind of lower section that juts out beyond the joint. So there's this little condyle that sticks up. It's hard to point. That I hold the magnifying glass. I'll try to point with this here. There's this little condyle here, this little extension of bone that attaches to the upper jaw, and then there's this section back here that extends beyond that, and then there's this piece here that sort of forms a strut and comes down and connects with the lower jaw behind the eye socket orbit. So keep that in mind, and then I am going to pull up a mammal skull. So here is the skull of an opossum. And unfortunately, the lower mandible has come apart at the center. And so I'm going to hold up one piece at a time, try to get this to occlude. So what I want you to notice is that, first of all, the teeth are differentiated into, we have our incisors in the front, and then we have canines, premolar, and then these are the molars back here. And in that reptile, remember that there was no differentiation, right? And so in the mammals, that is something that really helped to be able to eat different kinds of foods, because each of those teeth serve different functions. So the incisors are for kind of gnawing or grabbing plant matter and things like that. And canines for just grabbing onto things. So, you know, if you think of an animal chasing prey, it's going to just grab on with those sharp canines. And then the cheek teeth, the teeth that are in the back, are for shearing and also for chewing and grinding. And reptiles, in contrast to mammals, they don't really chew their food. They catch their food and then generally they swallow it whole, and so there's not a lot of mastication that's happening. Whereas with mammals, they really developed the cheek teeth, getting cusps and ridges that allow for different functions of shearing or grinding, whether you have a carnivore or herbivore. Other things I wanted to point out about this. So in contrast to that reptile skull, notice that the lower mandible is set into the zygomatic arch. So this is the cheekbone, and the orbit is up in here. Here's the orbit. And so that little condyle I pointed out extended and now forms really the joint here, and then what formerly extended back to the posterior end of the skull has disappeared, right? And we're going to talk about what happened to that. So I'm going to pull up a slide. So here's our reptile skull, and I'm just going to make this bigger. And what I want to show you is this bone called the dentary bone. And that bone is the same as this entire lower mandible. And so these bones back here, so the angular, the surangular, and the articular, they've disappeared. They've gone somewhere. And then the quadrate, which forms that little strut on the reptile that I showed you, has also disappeared, right? So we just have the dentary, and it kind of joins with this zygomatic arch, which we see here, this jugal bone. And go to the next slide. So here we see these bones are color coded, and this pink purple color corresponds with the dentary bone. And as I showed you, so this is Didelphis, this is our opossum, same skull I just showed you. This purple is the dentary bone, and here on the reptiles, the dentary bone is smaller, and behind it we have that angular, the surangular, and then we have the articular. And the red here is the quadrate, and then the blue is the squamosal. And the squamosal, you can see, has been retained in the mammals as part of the upper jaw, and in our opossum, it's gotten, it's a little bit bigger, and that's true for most of the mammals. And it is forming part of the zygomatic arch. So it's kind of fused with the jugal bone to come around and wrap around to make these strong cheekbones. Now, what you'll notice is that, so the green and the red and the yellow, which here on our Dimetrodon, which is a synapsid reptile, it's a mammal-like reptile, one of our ancestors. The quadrate, articular, and angular are back here in the posterior end of the jaw, but in the mammals, they've actually shifted position into the middle ear. And so, the jaw is really connected to the ear. It's not that far for it to move, but those bones shifted position and formed this structure of the middle ear that is more complex than the middle ear of reptiles. So in reptiles, there's this bone called the stapes that when sound bounces against the tympanic membrane, it causes vibration in the stapes, and the stapes triggers nerve cells to move around and send that message to the brain that you're receiving sound. In the mammals, having those three bones actually allows for greater vibration, and it allows mammals to have much more sensitive hearing and be able to pick up a wider variety of frequencies. And so that was really helpful for mammals, which early in their evolution were nocturnal, and most really still are nocturnal. Many are diurnal, and many are crepuscular, but in the early days of mammals, the reptiles were out in the day, and part of how mammals were able to carve out a niche for themselves was to be active at night. And so they couldn't see as well, and they needed to have really sensitive hearing. Additionally, that stronger dentary bone, so when you have one bone, it's going to be stronger than a bunch of bones fused together, and so it strengthened that lower jaw, and it also allowed for a greater area for attachment of muscles, and specifically for the temporalis muscle, which causes the lower jaw to move up and down, as well as bone side-to-side movement, which the reptiles really didn't need so much. And so here is an image, a couple images showing the, and I'm sorry, I meant the masseter muscle is the lower one, and then the upper one is the temporalis. These are your temples, right? Temporalis is up here and connects down to the lower jaw and kind of pulls it upward. And then the masseter comes across here. And so you can see on our lovely didelphis here that there's quite a bit of space for attachment of that temporalis, or I'm sorry, masseter muscle. And then on top, there's this ridge called a sagittal ridge or sagittal crest that allows for much more attachment of the temporalis muscle. And so those muscles got much stronger in the mammals and allowed for more forceful action of the jaw, and thus supported chewing and grinding and shearing and things that reptiles previously could not do. We can divide the skull into two main parts. So we have the brain case, or the cerebral skull. So the back of the skull, which contains the sensory organs, so ears and eyes and all the nerves that go along with those, as well as the brain case. And then the facial skull, which includes our jaws and teeth and the rostrum. And then inside the rostrum, we have all our nasal turbinates, these really delicate bony structures that provide lots of surface area for picking up scent. And in the mammals, so those two parts of the skull have evolved independently of one another in various ways to support different ecological niches. And we've ended up with quite a variety. And so I'm going to just show you some of the variety that we have. This is a domestic dog, by the way. One thing that you'll notice on this domestic dog is just how nicely articulated the joint is back here. And so you can see where that joint just sits at the base of the zygomatic arch, and that this extends up inside it, which was a little bit different from our this guy that just didn't articulate quite so well, wasn't as clear. Oops. Yeah, it's a little hard to get that in there because this guy is falling apart. And clearly this canine has well-developed canines, right? So we know it's a predator. And then it also has these teeth in the back called carnassials. So this is an example of where the cheek teeth differentiated to really support shearing of meat. And then on canines, there's also behind those, there's some flattened teeth, flattened molars that allow for grinding of bones. One thing to do is if you have a dog, watch your dog. If you feed your dog meat, they're going to go right to the back here and start trying to shear some of that with these carnassials. And if they're like chewing on a bone, they're going to probably be working back here. So some other interesting variety. So this is from a harbor seal. So really large orbits here, and you can really see those nasal turbinates, those really high surface area folded structures in here to pick up scent. And I have here pig. So unlike the other even-toed ungulates, these guys kept well-developed canines, which are probably, I don't know a whole lot about pig, teeth and whatnot, but I think it's an aggressive kind of thing for defense and for fighting among males. I have the skull here of a moose, so we just have an example of one that has gotten really, really large. And you can see back here these grinding teeth. There's also, these guys, just like deer, don't have incisors on the top. They just have incisors on the bottom. And they have this calloused section on the upper jaw, and they kind of just pull off, they grind, grab and pull off vegetation, and then they send it into the back, and they have this wide diastema or space between the incisors and the cheek teeth, because they just don't need to have those canines, and they needed to be able to extend that jaw outward, and that allows them to do this grabbing function and then send it to the back for grinding tough fibers. We have, this is a really interesting one. This is the skull of a dolphin. And this one, you can see that all the teeth are just in this straight row, and they're evenly spaced, and if the teeth were present, we would see that they're undifferentiated. So they're a lot more like a reptile. But these, a dolphin is, there was an intermediate stage in evolution where they were terrestrial, and they would have had differentiated, so their ancestors would have had differentiated teeth. But then when they went and they became marine, again, secondarily evolved to be marine organisms, just catching fish and then swallowing that fish whole and not really needing to do any chewing, the teeth reverted back to that really simple reptilian form, similar to our iguana. I have some other interesting ones here. This is another example where we have really simplified teeth, but interestingly, the teeth, there's a diastema in the front, so again, that space, and there are no incisors, and this is an armadillo, and you can see that the teeth are like very much like that iguana, and armadillos are insectivores, and so it makes sense for them to have really simple teeth. They're not doing that complex chewing and shearing kind of thing, just catching things and swallowing them. And then I'll hold off on showing any others until we practice some keying of the skulls. We're going to do a little bit of identification. One other thing I want to show you is that, so a change that happened in the skull in the evolution from reptiles to mammals is that mammals evolved to have milk teeth. And milk teeth it's baby teeth, and they are this first set of teeth that come in order for a mammal to be able to eat as it develops the jaw and the skull. And that allows it to be able to get enough nutrition as it's growing. And then once the jaw is fully formed, the permanent teeth come in, and that way they're able to occlude perfectly. And so, if we look at, so first of all, I'll show you this guy. This you can see these teeth. This is a baby coyote, and you can see that the molars, this is a carnassial, and you can see the molars have not erupted from the jaw yet. This jaw has quite a bit of developing to do, and then there's teeth that are set in there inside the tooth sockets. And let's see if they're going to show you. So here is the jaw of a fox. I'm not going to tell you which fox because we'll practice keying it. But what you can see is that the teeth just match up exactly where they're supposed to be, right? So really nice occlusion. Sometimes there are errors, like I have a malocclusion, meaning a bad bite, which is why I have braces, because that means that I cannot properly chew my food in the way that I'm supposed to, and ends up with uneven tension on the jaw and things like that with the masseter and the temporalis muscle, and thus TMJ dysfunction, temporomandibular joint. But this guy looks pretty solid. So I want to point out to you also the this is the these are called auditory bullae, B-U-L-L-A-E, and so an individual one is auditory bulla, and these are these little bulbous capsules toward the posterior end of the skull, where part of the middle and inner ear is located, and you can see that there's this hole here for the external ear. One other thing about skulls that I'll mention is I want to talk about antlers versus horns. And so here I have this is a buck that was given to me to the Sterling collection by a local hunter who used to teach here. And you can see that it has antlers. And I have here's another deer antler. And here is a antler. And you can see that this is quite large, right? And the thing about antlers is that they are grown fresh every year. They're made of bone, and then they're shed. And so they're used in the breeding season, and that's it. And so the bone grows incredibly fast. I've heard it's I think maybe the fastest growing bone in the animal kingdom. And it takes an enormous amount of energy to produce this every year, right? So horns have a bony sheath, or I'm sorry, they have a bony core, and then around that they have this keratin sheath. And you've probably seen just the keratin sheath hollowed out without that bony core, where people will use it as an instrument, right, like a shofar. But this is a permanent part of the animal. It's not shed every year. So the next thing that I would like to do with you all is do some keying of skulls. And so you should have received in the mail a packet that looks like this, key to the mammal orders of Vermont. And we're going to start on the first page, which is the key to the mammal orders. And so let's start with, let's see. I'm going to start with this guy. And so the first dichotomy here is there a wide diastema present between the incisors and the cheek teeth? Remember, the diastema is that space Here's our incisors, here's our cheek teeth. So yeah, clearly there's a diastema there. So that brings us to 2. And then it's asking us about the dental formula, and I haven't introduced that yet. So in a dental formula, you are counting the number of teeth of each type, so incisors, canines, premolars, and molars. And you're doing that on one side of the skull. And so you do top first and then bottom. And so this says incisors 0 over 3. So meaning that there are no incisors on the top, and then there are 3 on the bottom. And that is going to correspond with our artiodactyla, the even-toed ungulates. You can see that there are no incisors on that upper jaw, and then down on the lower jaw, we have 3 on, actually this is 4 on. Oh, it says, yeah, lower incisors resemble incisors, lower canines resemble incisors and look like a 4th incisor. So yeah, so on these guys we have 1, 2, 3 incisors followed by, this is a canine that looks just like an incisor and serving the same function. So no, it's not that. And then, so we go to the next one, and oh, and another thing on that, on 2A, is that it says orbit enclosed by a solid bony ring. So the orbit is the eye socket, and you can see that there's this solid bony ring. So that is in contrast to this guy. So let's look at how each of those characteristics contrasts with this. So it says incisors 1 over 1 or 2 over 1. And this one has 1 on the top, 1 on the bottom. So it's 1 over 1. And that is in contrast to this one here. And what I want to show you here is that we have 1 on the top, 1 on the bottom, but then there's these little peg teeth in the back. I'm going to find my magnifying glass to show you that because it's a little bit hard to see. But see those in the back? That is a characteristic of lagomorphs, or the rabbits and hares. And this guy that we're looking at just has 1 over 1. But that's still, so that's 2B. So 1 over 1 or 2 over 1 and chisel shaped. So these are, we call these chisel shaped. Orbit not enclosed by a solid bony ring. And so you can see here's, you know, our orbit, and it extends into this opening here with the zygomatic arch. So we don't have that solid bony ring. So that brings us to 3. 3A, incisors 2 over 1. We already know it's not that. Cheek teeth 6 over 5. Side of rostrum, an open lacework of bone. And I'll show you what that looks like. Lagomorph. So here we have, here's our rostrum, and the side is this open lacework of bone. A bony projection at rear of zygomatic arch. So that is, you can see this little bony projection here. And let's see. For this guy, we have incisors 1 over 1, and then cheek teeth never greater than 5 over 4. And so we're going to count the number of cheek teeth on the top, and it's 4. And then on the bottom, it's 4. And so it's not greater than 5 over 4, so that brings us to rodentia. So let's key out a couple more orders, and then we'll go into keying out species. So let's try this one here. So going back to 1, is there a wide diastema present between the incisors and cheek teeth or not? And there's not. See, it goes straight from incisors to canines, to premolars, molars. So that brings us to 4. And then total number of teeth equal to 50. or total number of teeth less than 50. And the one that's equal to 50 is didelphimorphia. Now, you might remember Didelphis, which was our opossum. And what we can do is count one side. And so we have 1, 2, 3, 4, 5 incisors, 1 canine, premolar, 1, 2, 3, 4, 5, 6 molars. So 5, 6, 7, 10, 13 on a side on the upper jaw. So 26 on the upper jaw. Then on the lower jaw, we have 3 incisors, 1 canine, premolar, and then we have our 6 molars. So we have 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait, is that right? Or are we missing? Oh, we're missing, sorry, we're missing a, maybe that couldn't be right. Yeah, this one has 4 incisors. And so it should have 12. It does. It's 12 on the bottom. And so that adds up to 50. So, whoops, sorry, trying to get this all set up over here. So 24 plus 26. And we have 50, and so Didelphimorphia is the order of the Didelphidae, which is the opossum family, and Didelphis, which is the genus for opossum. And all the other mammals that we have here in this part of the world are going to be less than 50. And so if we count the teeth on this one, we have 3 incisors, 1 canine, 3 premolars, it looks like, and then 3 molars. So 1, 2, 3, 4, 5, 6, 7, 10 on the top. And the bottom we have 1, 2, 11. So 22 plus 20, so we have 42. And so it's less than 50. So that takes us to 5. Canines longer than incisors, and that is absolutely true. Look at those canines, and here's our incisors. And so that brings us to 6. And I'll just show you that that is in contrast to our soricomorphs. And let me find those. This is one where I'm going to have to pull out the magnifying glass, and I also have to be very gentle. Delicate skull. So this is a hairy-tailed mole, and whoops, what am I doing? Put it on the wrong side. So notice that on this guy, the incisors are longer than the canines. It's got really short canines. So this is a soricomorph. You might also hear that order called insectivora. So this is an insectivore. Skull length less than 25 millimeters. 25 millimeters is very small. This is definitely greater than that. If you would like, we can actually measure it just to see how long it is. And it is, oops, just a second. So it's about 120 millimeters. So, and then incisors 3/3. Yep, that's what we found. And then molars without a W pattern. And so the W pattern is in, let me see, I have the skull here in this order. Okay, so this guy, so if we go to that last clue, so skull length for this one is less than 25 millimeters. So I'm going to measure that, and it is about 15 millimeters. Incisors 1/3 or 2/3, and where did I just put the lower jaw? So, glass. So here's our little skull, and you'll see in the front, it's got this kind of funny gap here, but it's not a gap between the incisors and cheek teeth like it is in the rodents. It's here in the front between the incisors, and you'll see that there's just one incisor on each side. And actually, I'm looking closely, and there's two. There's one big one, and then there's a little tiny one next to each of those incisors. It's probably pretty hard to see with the magnifying glass. So two on the top, and then we have on the bottom. It's very hard to see. Let me see if we're missing one. This one only has 2 minutes. Yep. So this one has 3 incisors on the bottom jaw. I don't think you're going to be able to see. It's really, really small. But so that's 2/3. And then it says molars with pointed cusps uniting to form a W pattern. And I'm going to pull this out and show you, and maybe you'll be able to see. Oops. That these have a little W pattern. Maybe that's visible to you, maybe not. You see that W? It's okay if you can't, you can imagine it. But we don't see that in our skull that we're keying in right now. This is what those incisors look, or cheek teeth look like, and there's not a W shape. So this leads us to carnivora, carnivores. Now that we've gone through these orders, let's go ahead and key out. Let's do our rodent here. So what we're going to do next is go to the order Rodentia. There's a separate key for each order. Oh, and I should, I want to say that this key was given to me generously by Steve Trombulak, who is a faculty member at Middlebury College and also teaches vertebrate natural history. And when I first started teaching this class, he gave me his mammal key, which I find to be a very good one. So I've continued to use it. So thanks, Steve. So here is, we're on our key to the Rodentia, and it says upper cheek teeth, 3 or 4 on a side. Remember, we counted 4, so we'll go to 2. Upper cheek teeth, 3 on a side or 4 on a side. We counted 4. We'll go to 13. Skull length less than 35 millimeters, or is it greater than 35 millimeters? And I can tell you right off the bat that it is greater, but let's just see what the measurement is. It's about 100 millimeters. Let's see, we were on 13. And so then that brings us to 14. Skull length is greater than 70 millimeters, so we go to 16. And infraorbital foramina, I have trouble pronouncing that word, because it's not how it's spelled. It doesn't sound like it's spelled. But so foramen is the singular, and this is a infraorbital foramen. So this is our orbit, and below the orbit we have this hole, and a foramen is basically, it's a hole in the skull where nerves and blood vessels cross through. And so this one is quite large, has a really large infraorbital foramen. And I'm going to find you an example of a skull that doesn't. So this is in contrast to this guy. So look at those minute infraorbital foramina. And so that leads us to 16b, greatly enlarged infraorbital foramina, Erythizon dorsata, North American porcupine, and that is exactly what this is. Let's do another. So let's do our lagomorph. And so let's go to the key to lagomorpha. And let me just make sure that I have both of my lagomorph spells here. I do. And so post-orbital processes flared outward from brain case. So processes are like bony protrusions. And so post, obviously behind orbital. So post-orbital, behind the eye, processes, bony protrusions, flared outward from the brain case and not fused with frontals. So the frontals are these bones here in front of the brain case. And it says at posterior tips of the frontals. And then the jugal, remember that's this bone here, this one, the front of the zygomatic arch, noticeably broader at center than at either end. And so let's break that down a little bit and take a look at this. We're going to compare two of them. So if you look at the top here, so this here, this little piece is a post-orbital process. And look at how this one fuses with the brain case. It's actually fused with the frontal bones at their posterior end because there's this really, it's hard, you're not gonna be able to see it probably, but there's a joint here where the frontals are fused to the brain case. And so really where that is touching is at that very posterior end of that frontal bone. And then this one in contrast, here's our post-orbital processes, and notice that they flare outward from the brain case and they're not fused to those frontal bones. And then it says jugal or malar, noticeably broader at center than at either end. So let's take a look at this bone. And so notice that there's this little bit here where it gets wider. It might be hard to see, but it's a little bit wider at the center. And on this guy, it's not. It's pretty consistent. It doesn't have like a little wide spot. And so that tells us that we are not looking at a snowshoe hare. It tells us that this one here, so this is the second one I pulled out, is a snowshoe hare, right? Because it's got those fused post-orbital processes, and then it has that wide-end spot on, I want you to be able to see that. See that little wide spot right there? That wider spot on the bone. And so that means that we go to 2, and then it says suture line between nasal and frontal bone, smooth, or is it jagged? And so that is, it's gonna be a little hard to see, but right in here, so we have, this is the nasal bone, it goes across the top of the rostrum, and then we have those frontal bones, which are like the forehead. And so the suture line here is what we're looking at. And if I look at that, it looks almost a little bit jagged, like around the top edge, the posterior edge of that bone. But then along the main part of that suture, it's very smooth. And so that brings us to Silvolagus floridonus, which is the eastern cottontail, as opposed to the New England cottontail, which is much less common. And I will say we don't have eastern cottontails here in the Northeast Kingdom. I've never seen one here. Maybe they're here once in a while, but we mostly have an abundance of snowshoe hare. So we'll do one more, And then I'm going to send you on your own to do some keying. All right, so let's look at this carnivore that we found. And so we'll go to the key to the carnivora. And it says, no carnassial teeth present. So remember that the carnassial teeth are those shearing teeth. And in the milk teeth, they are formed by the fourth premolar on the top and on the bottom. But then when the molars come in, the permanent teeth, they bring in this big, first molar that forms the bottom carnassial. And so this one does have carnassials, but I'm going to find one that doesn't to just show you in contrast. Okay, I'll show you a couple. So this one, notice that, so this is also a carnivore. And when I say carnivore, I'm talking about the order, because yes, the animals in the order carnivora are for the most part carnivores, but some of them are omnivores. And what we're looking at right now is actually an omnivore, and but it is in the order carnivora, so I'm calling it a carnivore. So just to make sure that you're clear on that. But what you'll notice is that the cheek teeth, there's no carnassials. They have these, they're a little bit sharp, but then they have a flat surface on all the molars. They're a lot more like our molars. And this is a raccoon. And you know that raccoons eat just about anything, right? You find them in your garbage for that reason, because they will scavenge for whatever they can find. And here is another omnivore that you can see does not have carnassials. It has these flattened molars with a little bit of point to them, but they're not like purely for shearing. They have those flattened surfaces. This is a bear cub, and so this is this cub still has its milk teeth. But you can see those cool flattened surfaces because the bear, again, is an omnivore. It's not, purely a carnivore. It eats a lot of plant matter. Another thing you'll notice about this, you can see the baby teeth. So check this out. So you see this canine coming in here, but notice that the canines are not as well developed as they are in our dog has super well developed. For our raccoon. So here's a raccoon, and you can just see that the canines, it has canines, but they're not as well developed because it's not actively hunting and grabbing a lot of animals. It's mostly scavenging. Where were we? We were on this guy. So that brought us to, okay, so carnassial teeth present is fourth or last upper premolar, and that is correct. So we have 1, 2, 3, 4, and that's our carnassial. And then the first lower molar. So 1, 2, 3, 4 premolars, and then this is our first lower molar, and that is our carnassial. Remember that behind the carnassials, we have these kind of flattened teeth on this family, which is, this is a canid. So we'll find that out in the key. So it's in the dog family, and dogs tend to have, they'll have that flattened grinding molar in the back. In contrast to that, I'll show you. So here is the upper jaw of a cat, and notice that there are no flattened teeth here. It's purely for, these are all sharp, and for those rear teeth are just for shearing. And it's got this greatly reduced rostrum, right, really short, and that provides a lot of pressure for the jaw to close. They have really strong jaws that are really built for ripping, pieces of meat, flesh. Whereas dogs are going to, scavenge and grind on bones and stuff, whereas cats are eating like live. They're hunting and not like grinding the bones and such. Or eating a lot of vegetation, right? My cat eats a lot of grass, but they may eat some plant matter from time to time. Kind of helps their digestion, but dogs eat quite a bit of fruit and whatnot. So let's see. So that brings us to 3. Then it says molar teeth with no crushing surface and all of cutting type, right? That's our cat. Cheek teeth 3/3 or 4/3. And so, yeah, we have 1, 2, 3 on the top. Now compare that to 50, right, in the opossum. Quite a difference. Post-orbital processes relatively long, almost meeting zygomatic arch. So remember, these are the post-orbital processes, and look at how long that is. It almost meets that zygomatic arch, right? There's only this little space between, as compared with this guy, and that post-orbital process is not nearly as long, and there's a much wider gap between that and the zygomatic arch. And then it says upper molars progressively, I'm sorry, I was on the wrong number, 3. So we know it's not 3A, so 3B, molar teeth, at least the last molar with evident crushing surface in addition to cutting edges. Yep, we saw that. Cheek teeth 4/5, 5/5, 5/6, or 6/7. So variable, but let's see what we have. We have 1, 2, 3, 4, 5, 6 on the top. And then we have 1, 2, 3, 4, 5, 6, 7. So 6/7. And then post-orbital process is relatively short, not almost meeting zygomatic arch. We already went through that. And this takes us to 7. So tooth rows and rostrum relatively long. Tooth rows and rostrum relatively long. Auditory bullae inflated. So we see these are kind of inflated. Cheek teeth 6/7, and that is what we got. Now I'm going to show you a animal to. So let's. That's not a good. Wasn't the one I meant to grab. Okay. So this guy, in contrast to that, tooth rows and rostrum relatively short. See how this is the, we have the orbit and the eye socket here, and it's got this really short rostrum. Brain case large and flattened. Check out that large flat brain case. Auditory bullae generally flattened. So they're back here, and you can see that they are pretty flat. They're not inflated like this. And then auditory, I already read that. So cheek teeth 4/5, 5/5, or 5/6. And this one has 1, 2, 3, 4, 5 over 1, 2, 3, 4, 5, 5/5. And so that would bring us to 12, which would lead us to the Mustelidae, the weasel family. And all the weasels have that large flattened brain case and that shortened rostrum. So that's a really good way to identify them. And so this guy, we have our relatively long rostrum, and so that brought us to 8. Skull length greater than 160 millimeters, or is it less than? So we can go ahead and measure. And this is about 120 millimeters. And so that means that we're going to go to 8B. And then it says dorsal surface of post-orbital process, slightly concave. And so what I want to show you, so the dorsal surface is here. And, you know, this is our post-orbital process. And see how there's like this little, I can stick my finger in there, there's this little gap. So it's a little bit concave, and I'm gonna contrast that with our, this is a coyote. And this coyote, the post-orbital process is rounded, convex. It's also larger. So that brings us to 11. Cranial ridges form a narrow V. So these are the cranial ridges, also called the temporal crests. And in this case, it's asking us if those form a narrow V or if they form a broad U. And I'm going to show you one that has a narrow V. So look at how those ridges form a V here. And that is different from this guy, where it forms this broad U. And then, so shortest distance between post-orbital, so this would bring us down to 11B, right? We have our U, shortest distance between post-orbital process and zygomatic arch, 9 to 10 millimeters, versus is it 16 to 18? So we need to measure that. And so I'm measuring right here between the post-orbital process and the zygomatic arch, and it's about 10 millimeters. And so that is in line with 11B. Contour of lower jaw not curved and with a posterior step. So here is, I'm going to show you two different jaws of canines, and look at how this is curved upward a little bit in comparison with this one, which is very flat. And then notice there's this little step at the back, touching the wrong thing. Right here, there's a little step. That's the posterior step they're talking about. So that brings us to Eurocyon Cinerio argenteus, which is our gray fox. And the other one was Vulpes vulpes, the red fox. You can see that they're fairly similar, but really distinctive is that U shape on the temporal ridges on our gray fox versus the V shape on the red fox. And also the red fox is a little bit longer. It's a little bigger animal. So that's how to key out skulls. And you can see there's a lot of terminology. And to help you in the back, there's a glossary. And there's also some really nice labeled images. There's instructions here on the dental formula. If you just look up dental formula in your glossary. And this part is really helpful. There are skulls with the bones color-coded and labeled to help you in identifying them as you go through the key, as well as other parts. One thing that I forgot to mention when I was talking about skull anatomy is we've talked about the secondary palate, and I want to show you what that means. Here, okay, so let's look at our bear cub. And what I want to show you is that here there's a suture line. Okay, and then we have these foramen, right? Foramina, these holes where nerves and blood vessels come through. And then there's this bone that extends all the way back to here, and the nasal cavity runs through here. And this back part is the secondary palate, and this front part here is the primary palate. And so in the mammals, that secondary palate evolved, and that allowed for breathing and chewing to occur at the same time, which was really important for mammals that spend time chewing, unlike the reptiles, and that also need to be able to get oxygen all the time in order to fuel their high metabolism as endotherms. So your task is going to be, I'm going to share some pictures of skulls with you. And your task is to key those out. And then what I would like you to do is once you key them out and you get to the species, I'd like you to look in your mammal field guide and take a look at the species account and the plates for that particular species. And there will be a worksheet where I will ask you to identify the species and also provide some information about them based on what you find in your field guide.